of the fast diffusion equation. And these are John works with my former postdoc Sung Ho Kim and Soo Jun Chim and Jinhwa Park, all from Korea. Now the equation UT equals to Laplacian UM arises in many physical models and has many geometric applications. Where when M is bigger than 1, is called a porous medium equation, and it arises in the flow of gases through porous media or oil passing through sand, etc. And recently, Huang, Pan, and Wang, and Lotao and Zhang, and they have shown that the fast diffusion equation is also the large time asymptotic limit solution of the compressible Euler equation with damping. And Gross and Zavarani also shown, and Choi and KMD also shown that the fast diffusion equation also appear as a nonlinear diffusion limit for the generalized Kellerman model. For M equals to 1, this is the well-known heat equation. Now, when M is between 0 and 1, the equation is called a fast diffusion equation. And when M is n minus 2 over n plus 2 and n bigger than or equal to 3, the fast diffusion equation arises in the study of a Yamabe flow of GT equals to minus RG on Rn, where R is the scalar curvature of the metric G at the time t. And in fact, if we write, because it's conform, if it is conformal, we can write G as u to the power 4 over n plus 2 dx square, where dx square is the Euclidean metric. Then this is a metric on Rn, and then if we suppose that this G evolved by the Yamabe flow, then since the scalar curvature can be written as minus 4m minus 1 over m minus 2 u inverse Laplacian u m minus 2 over m plus 2. If we substitute this back into this equation, we get that u satisfy ut equals to m minus 1 over m Laplacian um, where m is n minus 2 of m plus 2. And this is equivalent to the fast diffusion equation after rescaling. So if we rescale in the time, then this would disappear, and then it would become the same as this equation. Now, the reason why this equation is hard to study is this. If we always write the equation in the divergent form, then this can be written, the Laplacian um is equals to m divergent um minus 1 grad u. And then u to the power m minus 1 is the diffusivity of the equation. And the diffusivity will goes to infinity if u goes to infinity, or goes to 0 as u goes to 0 when m bigger than 1. And then it goes to 0 and infinity as u goes to infinity, and u goes to 0 where m is less than 1 and 0. So this means that the equation is not uniformly parabolic. And hence, the standard theory of parabolic PDE cannot be applied directly to this equation, and this makes the fast diffusion equation a hard problem. Well, recently, there are a lot of interest on the study of a singular diffusion equation of a Yamabe flow, a fast diffusion equation for the case m is less than n minus 2 over n. Because in this range, the equation has many phenomena. The solution has many phenomena which is different from the case m bigger than n minus 2 over n. And one important result is by Wasker and Winkler, and they studied the one-point singularity solution of fast diffusion equation in the bound domain. And they found that if the initial value, if omega is a bound domain and u0 is the initial value, which is sandwiched in between some constant x to the power minus gamma 1 and constant times x to the power minus gamma 2, where gamma 1, gamma 2 are some positive constants, then the solution will have will be singular. The solution to this initial boundary problem will have a solution, and this solution has has the following property. If the blow up rate is less than 2 over 1 minus m, then there is immediate regularization occur. That means that although the initial value blow up at the origin, the solution will remain bounded for all positive time, and so can be extended to a solution on the whole domain. And however, if the blow up rate is bigger than 2 over 1 minus m, but is less than m minus 2 over m, then they found that the solution U exhibit an infinite time blowdown behavior. That's to say, the solution U will go to infinity. There is a time capital T, the solution would blows up at the origin. But however, when T is let me see. But however, that if we for all points that is away from the origin, if it goes to infinity, the solution becomes the solution is finite. And then if the blow up rate is bigger than m minus 2 over m, then we found that then they found that you blow up in infinite time. That's to say, the solution goes to infinity everywhere in the domain as the time goes to infinity. So after the result, a natural question to ask is that whether we will have a similar results when we have a finite number of singularities. That is to say, the solution blow up a finite number of points. So this is a first step to generalize the result. So we answer this question in the affirmative. Now let me start the framework. We let for n bigger than or equal to 3 and omega be a smooth domain, and we let A1 up to AI not be points in omega, and we let the punctured region be omega hat. There's omega minus these points, and Rn hat as the Rn minus these points. And then I let delta 0 be the minimum of the distance between these points. All right, so this is well, one third of that. Then we found I and my postdocs found out the blow up rate of such solutions near the blow up points. And when m is less than m minus 2 over n, existence of single solution was proved by me and Song-Ho Kim. When the initial value also satisfied this, that is, if the initial value blow up at the weight x to the power minus gamma I at this kind of blow up points, when gamma I is bigger than this constant, then we found that this the blow up solution exists. But later we we found a more general result that because in this paper we only get the result when gamma I is very large, but we cannot recover all the results of Vaska and Winkler. But in the later result, we recover all the result of Vaska and Winkler for solutions with a finite number of singular points. And we proved the existence of solutions in the punctured domain such that the solution blows up at this point at this prescribed points when m is less than m minus 2 over n, and the initial value is LP log, where p is bigger than n over 1 minus m over 2. And we also require the initial value to blow up at a rate of x minus ai to the power gamma I at each of such points. And then the gamma I has to be bigger than 2 over 1 minus m. And we also obtained the large time behavior of such single solution. And later in 2020, I also proved the uniqueness of such singular solution. That is to say, given initial data satisfying this, the solution, the blow-up solution is unique. And we also found the asymptotic large time behavior of such solution. Well, what we get is this. We get that if the initial value is bigger than some positive constant, and the initial value blows up at a weight x to the power gamma I for each of the points, and one of the blow-up weight is bigger than m-2/m, then the then the singular solution would converge locally uniformly on every compact set to infinity. That is to say, the solution would blow up at every point in the domain as t goes to infinity when one of its blow-up weight is bigger than m-2/m. There is so what about if all the blow-up weight is less than this value, what happens? So we answered this question in and got the following result. We found that when u is bigger than some positive constant on the domain, and u0 is bound between two power of x to the there's x to the power minus gamma 1 gamma I, x to the power minus gamma I prime, where gamma I prime is in between these two values, then we find that u actually converges in C2 for any compact subset to a harmonic function. Well, more precisely, we prove the following existence and uniqueness and convergence result. So the result we obtain are the following. We obtain that when n is bigger than 3, well, why we are only considering n equals 3? Because when n equals to 2, the Yamabe flow and the Vichy flow are the same, and then we just ignore the case. So when n bigger than 3 and when n equals to 2, the only choice is when m equals to 0, and then the equation becomes the Laplacian log u. So this is which has very different properties, so we just ignore it. So when n bigger than 3 and m is less than m-2/n, and then this is delta 1 is less than the distance of between the points. If the boundary value is L infinity, is L infinity, and the initial value is also local LP, where P is bigger than n over 1 minus m over 2. Well, we require this condition because this would make the solution have a local has a local L infinity regularizing effect. Let me just tell you this. Yeah. Do you see the whiteboard?
No.
No? Okay. No. Let me see how to do it. Okay. See. Well, anyway, let me just forget about it. Anyway, then let's see, wait. Well, anyway.
Maybe you can add new pages after that.
Let me see. Oh, okay. I know how to do it now. Now, do you see the whiteboard now?
Oh, okay.
Now you see that if u0 is the value here, if the value is belong to LP log, as for a parabolic equation, we always have a time lag regularization. That's to say, if there is a positive time, then for the P satisfying n over 1 minus n over 2, then there is a, by means of Moser iteration, you can find this solution here is L infinity. So this is called the LPL infinity regularizing effect. So this is by Moser iteration. So let me just okay. So that's the reason why we use this, because then the solution will be locally L infinity away from the singular points. Now, if the initial value is bigger, has the Baroque weight x to the power gamma I, then we can prove that there exists a solution to this to the equation which blow up at this kind of points, and then the solution, and then the U has the behavior that is blow up at the weight x to the power minus to the power gamma I. And moreover, if there exists a constant d0 such that f is monotone decreasing, then the solution will satisfy the Aronson-Bell non-equality. The ut is less than u over 1 minus m t over t minus t0. Well, if for the particular case of the Yamabe flow, then this actually corresponds to the scalar curvature positive. So, and then we have a similar result for the existence of solution in the whole domain. That's to say, if the initial value satisfies this kind of Baroque weight, then we can find the solution that blow up, and that the solution satisfies the Aronson-Bell non-inequality. And then here is the comparison principle. That means now we prove several comparison principles. If we first we have a stronger condition on the initial value. Let's say if F1, F2 is C3 and L infinity, and then if F2 is bigger than F1, and then U02 is bigger than U01, and then both of them have this kind of blow up weight. The initial value have this kind of blow up weight at the origin. And then we only require the condition that this is bigger than 2 over 1 minus m, because this is because as Wasker and Michel shows that if this is less than this, then the solution will immediately smooth at the singular points. So this is a necessary condition for the blow-up solution to exist. So if U1, U2 are the solution of of a Dirichlet problem, of this Dirichlet problem with the boundary value being equals to F1, F2, then the blow-up solution would also remain one less the other. And also, then we found that the solution would be bound above by the upper bound of initial value too. And also, we have a comparison of a solution. And then if we weaken the condition on the boundary value, say if we only restrict it to be L infinity but not C3, but then this is sort of like the Heisenberg's uncertainty principle. If we weaken the condition on the boundary data, then we require the initial value to have a stronger assumption. So the stronger assumption is that we require that the upper blow-up weight to be less than n minus 2 over m. So under this additional condition on the initial value and a weaker condition on the initial data of only L1, we also have the comparison theorem as before. The U1 is less than U2. So in particular, that means that the solution is unique if they have the same boundary value. And for the uniqueness in the whole domain, because we need to control the behavior at infinity, so we need the boundary value to be behaved in some good manner. So this is the criteria that we found. If the initial value differ from some constant, the differences is in L1 on the exterior of in the exterior domain, and then U0, U1 is bound between this, have this kind of growth rate, and then we require that this to be less than n. Well, the problem is still open when it's bigger than n. I don't know how to do it. And then then the solution will be bigger than U0. And we prove that there is a L1 contraction for the solution. There's a uj minus mu0 less than the initial value, u0j minus mu0. And then we also found that there is a comparison. There's u1 less than u2. Well, for the asymptotic large time behavior, we got the following results. This to say, with a similar condition as before, and then if U0 is brought up at this rate, and then we require that the broad weight is less than n, then and then the boundary value goes to the mu0 uniformly. Then we found that the solution also goes to mu0 uniform on any compact set away from the singular point as t goes to infinity. And then we try to change the condition here. Then then we found out that if we change the upper bound of the broad weight to this, then and then with the corresponding changes in the on the boundary behavior of the function f, there's ft is L1 and f bigger than mu0, then we can, and f xt goes to mu1, where mu1 can be different from mu0, then we also have a convergence of the solution to mu1 on any compact set away from this as t goes to infinity. And then another asymptotic behavior is that when the solution is bound between these two broad weights, and then the mu0 and then the gamma I prime is bound in between these two bound, 2 over 1 minus m and m minus 2 over m, and the initial value bigger than equals to mu0. This is then if fxt converge to some function g in C3, then the solution would converge to the solution of the harmonic equation Laplacian phi equals phi, the boundary value is gm. So from all this theorem, we see that the solution actually for most cases would converge to a harmonic function with a boundary value equals to the limit of the boundary value of a solution. And then how about in the punctuated plane? We also have a similar convergent result, but now we require that the broad weight is less than n. And because we need to control the behavior of a solution away from the in the exterior of a compact set, so we impose an additional condition that if U0 must be less than some constant when x is large. And also we require the U0 as before is bigger than some constant mu0. Then and also we also but then we also need the U0 convergent weight to this constant at infinity. So the condition is this, is that the integral of Rn minus Br1 of U0 minus mu0 dx is finite. So what this says is that in average sense, if we change it into spherical coordinate, what this says in this sense is that U0 converge to mu0 in average sense goes to 0 as the radius goes to infinity, right? Because if the integral on the sphere does not goes to 0, then this integral will become infinity. Then we find that the solution will go to U0 mu0 as t goes to infinity on any compact set of the punctuated plane. And then we try to see whether we still have such convergence under different condition on the U0, and we found such a condition. That is to say, we can when U0 is is in between these two familiar bound, that the Broadway is in between these two familiar bound, then because we have weakened the condition on here, then we need a stronger condition on the initial value. So that so now we require that the U0 converge to mu0 uniformly on the n-1 sphere as R goes to infinity. Then under these two conditions, then the solution will still goes to mu0 as time goes to infinity. And then we can see that there are convergence when in all the cases that when the Broadway is less than n-2 over m. So one will ask what will happen if any one of the index is bigger than n-2 over m. Then the answer is this: if one of the index here, if a solution at one of the point, if the initial value at one of the point blows up at a weight bigger than n-2 over m, then the solution would go to infinity as t goes to infinity. And then we have a similar results for the solution in the punctuated plane. That is to say, if one of the if the initial value blows up at the one of the point at a weight bigger than n-2 over m, then the whole solution would blows up as time goes to infinity. So from here we found that in many cases the solution will converges either to infinity or converge to some constant or to some harmonic function as time goes to infinity. So we will ask whether there are solutions with other types of behavior, and we prove this result, the following result. We find that actually there exists initial value such that the singular solution will oscillate between some constant and infinity as t goes to infinity. So that means that there are depending on the initial value, there is a large spectrum and variety of asymptotic behavior when the time goes to infinity. So another lateral question is that now in all the above result, we have assumed that the U0 bigger than some positive constant. So well, it is natural to ask what will happen if we remove this strictly positivity away from zero condition. That is to say, if this condition is, if we do not have this condition, what happens? So we found out that clearly if we, for the particular case when gamma equal n minus 2 over m, we found out that a x to the power minus n minus 2 over m is a particular solution of the fast diffusion equation. And then is the well-known singular Baron-Beck solution. There is that looks like some constant times capital T minus small t x square to the power 1 minus m. Then this solution is also a singular solution of the fast diffusion equation. But then this solution do not have global existence of solution, but vanish at a time t. So that means that if we remove this condition, the behavior is drastically different. The solution may cease to exist after some time. So recently, I found out that there is a guy in Hong Kong UST, Jinjiang Xiong or Xiong Jinjiang, or hard to pronounce. So they study the extinction profile of a solution when the initial value looks like some constant x to the power minus 2 over 1 minus m. That's to say, they try to look at the solution that behave like this one in their recent paper in ACAF. And then I and Sujin Kim study the asymptotic the existence of solution of equation U0 that blows up, that behave like this way, with initial value that is bound between these two guys in the whole domain. Because previously we required this to be true only in the vicinity of a singularity, but when it is away from singularity, we require it to be positive, to be bigger than some constant, positive constant. But now we require this condition in the whole domain. Then the solution is very different, and it is actually a self-similar solution when it is equal, and when it is not equal, it is bound by the self-similar solution of the equation. And then recently, I and Jinhua Park proved that the other case, when, you know, previously we always study solution in between here, but when gamma is equals to this guy, or some, when the exactly equals to this guy, or some times some log, then that is not known. So what we found out that there are existence of solution which looks like self-similar solution of this form, uxt equals to e to the power minus gamma alpha t f e minus beta t x, which blow up at the origin, and then the f is supposed to satisfy this equation, this degenerate elliptic equation, or equivalently this equation, where alpha and beta are related in this way, and both index are negative. Then we found that there exists a solution, unique solution to this guy, where the f looks like behave like this, close to the origin. That's to say, r square f 1 minus m over log r minus 1 tends to a constant. That's to say, FR looks like 1 over log R over R squared to the power 1 minus m. That is to say, it behaves like the initial value behaves like this one with gamma equals to 2 over 1 minus m. And then recently, I just was told by Jin Takahashi that M. Filler, McConvey, Jin Takahashi, Ayagida obtained the following result. they got a result that says that if f is a C2 function on the sphere, and gamma bigger than 2 over 1 minus m, and gamma satisfies this for some constant, and then f also satisfies this guy, then if the initial value behave like this, if the initial behave like this and strictly away from 0 and L infinity, then they construct a solution which have this behavior for all positive time. Then this looks like this. And then previously, M. Fuller, Takahashi, and Yalagita also study. They also found out when M is bigger than M minus 2 over M, there exists solution with moving singularity. There's a solution. The singularity will not be a straight line in the xt plane. That is to say, the singularity will move. There's as time increase, t increases, the point a1 up to an all moves with time. And then because we still have some time, so we can just give some sketch of the proof. So we sketch of the proof of theorem 1. Theorem 1 is the existence of solution. Let me so how to prove the existence of solution? As usual, you know, because the conductivity is can be 0 or infinity, so we have to try to make it away from, to make it uniform elliptic, to apply the uniform elliptic theorems. So what we do is that we do a two-step regularization. The first one is that we take the initial value, we chop off at m, and then we add a small constant, and then the same for the boundary value, we just add a small constant. Then we try to solve this equation. Because this equation is then the initial value is not equals to, is strictly away. There's on the parabolic boundary, the value is strictly away from 0. Then we can rewrite this equation as a non-degenerate equation, and then we can solve this equation. Then we get a solution which is by the maximum principle will satisfy bigger than epsilon and less than this guy. And then we found that this guy will satisfy the Aronson-Bannon inequality if f is monotone decreasing on t. So how to prove the Aronson-Bannon inequality is that we write ut over u as a new function and find out the equation for ut over u. And then we found out that and apply maximum principle to the function ut over u. And then we get this inequality. And then after this, we try to let epsilon goes to 0 and m goes to infinity as usual. But when we let epsilon goes to 0, we can we see that by maximum principle, the u epsilon m would goes down to 0. But the u epsilon m will be decreasing as epsilon goes to 0. So we need to show that this the limit u epsilon m as epsilon goes to 0 won't go to 0. So we need to find a lower barrier. But we found out that there is a that this cannot happen, because we found out that we prove a result that if u epsilon m as epsilon goes to 0, if this vanish at one point, then this will vanish in the whole domain. But then the initial value is not equal to 0, so you get a contradiction. So this guy is always positive, and then we try to, and then after that we let m go to infinity. But when m goes to infinity, because as what I said before, there is a local LPL infinity regularizing effect. So this guy is uniformly bound above on any compact set that is away from the time 0, from time 0. So this when m goes to infinity, this would have a limit, and that limit is the UXT, is a solution. So, and then we want to get a control on the blow-up weight, and then we find, and then we try to prove that this has this kind of blow-up weight. You know, this, as usual in parabolic PDE, we try to construct an upper barrier function, and we found out that this guy, well, after tedious computation, we will find out that this guy is a super solution of the fast diffusion equation. Now, this guy has a good property that when x equals to delta 3, that this is infinity. So we can compare the solution, this upper solution with this guy at x equals to delta 3 and at the initial value. But for the initial value, we can choose A0 sufficiently large that controls the then if we choose A0 bigger than this guy, delta I lambda I prime, then because of this, they have this kind of same blow-up weight at the origin. But if you choose this constant bigger, then we can apply maximum principle. Well, we can apply maximum principle because this epsilon m is bound between these two. So this then we can use the usual maximum principle and then compare this, and we get this bound. And then this bound we just for fixed time we just this can then be changed to a constant when t bigger than less than equals to some capital T. So this will give you an upper bound on the solution, upper blow-up weight on the solution. So how do we get the positivity estimate? The positivity estimate is this thing. Well, basically, we try to construct a function, a test function. The test function that looks like x to the power minus beta 1 for beta 1 in some appropriate value when x is small. And then I just try to multiply this solution with the test function x to the power minus beta 1. And then if we differentiate this, and then we can get some equation. If I differentiate this respect to time, and then I get some PDE, but then after solving this kind of equation, we found that this satisfies this equation. But then if we have x to the power minus beta 1, and then we know U0 well, blows up, well, there is a lower bound, right? As before, there's a lower bound, some constant over x to the power gamma I. So if we multiply it, we found out that this guy is, when epsilon equals 0, m goes to infinity, this is U0. But U0 times this guy, if we integrate this guy and we found that this is infinity. If this is infinity, that means that this one is infinity. So this is infinity only if the solution blows up at the origin. Well, actually, from here one can estimate the blow-up weight, the lower blow-up weight. So this is what I say. And then the next step is that we use a result by Carlo-Koenig. Well, if U0 is if the initial data and U is a bound solution, then it is known that the solution that it can be used by using a similar method as what Carlo-Koenig did, that the non-tangential limit of the solution is equal to 0 x0 when x is a point of density. That's to say, we would like to know the behavior of a solution point-wise close to the close to t equals 0. Then if x approach x0 along a parabola within a parabolic cone, then then we have this value. Then we can compare. Then after this, we can compare then we see that the solution. Then we can compare and apply and try to use maximum principle on u and some constant times x to the power minus gamma I, because we can choose C1 appropriately, because we know that u is u satisfy this guy, so this is strictly positive. So if for when it is at a fixed distance from the blow up point, so if this is strictly positive, then we can by choosing C1 appropriately small, then at some fixed delta 2 distance, then this is strictly bigger than u, strictly less than u. So we apply maximum principle and we get this result, something like that. So we still have so I'm supposed to talk for 45 minutes, right?
Yes, but if you need more, it's okay.
Maybe I just skip. Then I can go to. Let's see. Then because of time constraint, I must stop here and I let you guys see the last page. Yeah. Okay. Thank you. Any questions?
Yeah. All right. Thank you. Thank you, Professor.
Yeah.